Thank you very much, Stefan. Thank you all for coming. Yeah, I hope it's not a done deal, but we'll see. So I'm Keith. I'm here to talk about transport architectures for an evolving internet. And what do I mean by that? How is the internet evolving? I think I first got on the internet a little more than 20 years ago, and I think if you look at the sort of traditional 4 layers of the internet stack, we've seen dramatic change over the last 20 years in sort of all 4 layers. So at the bottom, at the link layer, what do we have now that we didn't have 20 years ago? We've got Wi-Fi and cellular networks and super fast data centers. Almost everything is different. And how about one layer up? What has changed? We now roam all the time now. We change our IP addresses regularly. You guys all have your MacBooks here. I see a few PC users, and you probably change your IP address all the time. That's something new at the network layer. At the top layer, the application layer, what applications do we have now that we didn't have 20 years ago? Pretty much all of them. We have this thing called the World Wide Web that's quite popular, and streaming video and sort of progressive download video like Skype and FaceTime. So we've seen changes in all those layers. How should the transport layer adapt to changing behavior in the layers below and changing requirements from the applications above? How should those protocols react? So that's sort of what I'm here to talk about. One possibility is to say, they're not going to adapt. The transport layer protocols are not going to adapt to change at the layers below. Instead, what we're going to do is just, if the internet evolves too much, we'll just throw out our transport layer protocols and we'll just make new protocols. And that might seem kind of silly, but in fact, it's been a very successful strategy. If you look at just one thing that the transport layer does, what I'm mostly going to talk about is the job of dividing up the internet, or what we call congestion control. This is part of the transport layer to decide how we'll divide up the resources of the internet. And if you look at the seminal schemes of the 1980s, the TCP Tahoe scheme, these schemes responded to the congestion collapse on the NSF net of the 1980s, and they were followed up with lots of research in the 1990s, and this new Reno algorithm is still the algorithm that's used in the iPhone and in Mac OS X. And then in the 2000s, there was a whole wellspring of research about TCP over wireless networks and the high bandwidth delay product networks. And then even in this decade, we're seeing new schemes from Google, and this one is used in BitTorrent, LEDBAT, to handle the problem of buffer bloat and all kinds of new problems that we have now. There's like 40 algorithms that we use in TCP to control sort of how we divide up the resources. And I think actually, in the aggregate, these algorithms may be among the most widely used computer programs in the world. In fact, I'm curious, can anyone here think of a computer program that is more widely deployed than these guys? Maybe not. All right, so this is the most widely used computer program in the world, as far as I can think of. And I'm actually only showing you part of the story, because these are the algorithms that handle resource allocation sort of end-to-end, with the intelligence at the endpoints. There's actually a whole parallel body of literature which says, what if we put the smarts inside the network? We put intelligence on the routers and the gateways, the sort of in-network protocols. And there's a whole other parallel body of literature about those algorithms, data center, TCP, and XCP, and all kinds of algorithms that put intelligence inside the network. So there's like 40 of these algorithms, and every time the internet evolves or we have new kinds of application demands, we just make more new algorithms. But this is a little tricky because when we make these algorithms, we don't always say why we made them as they were. So if we had to make a decision between the default in Linux, which is called cubic, or the default in Windows, which is called compound, how can you decide which one you should use? Why are these different at all? Do they try and achieve different things on behalf of the application layer above them? Or maybe they make different assumptions about the layers below them? It's really hard to say. So as a result, when we make those lower layers, if I'm making a new sort of Wi-Fi or a new kind of cellular network, I never know what assumptions the transport layer is making about me. What assumptions does the transport layer make about the lower layers? We're never quite clear about that. We can say, cubic does X or new Reno does Y. It's hard to describe what does new Reno think the network is going to do when it sends a packet. And as a result, the sort of evolution of the link layer and the subnetworks is constrained by this sort of fuzzy understanding of what the transport layer thinks. So for example, we're told that the transport layer doesn't like it when packets are randomly dropped, as can happen on a wireless network. So as a result, these network layers, like Wi-Fi and cellular links, they tend to try and mask that stochastic loss. And you end up with really long delays, like on a smartphone. We'll see that later. We're told that the transport layer, probably doesn't like it when packets are delivered out of order. The TCP will freak out when that happens. So as a result, the network layer almost never uses any sort of parallelism. It's rare that you get packets routed over multiple paths within a flow, because if you do that, it's possible they might arrive out of order. Even though it would be an optimization in some sort of abstract sense, we don't do that because we think the transport layer won't like it. In fact, our summary of the fuzzy specification that the transport layer imposes on the lower layers is like really long and vague and complicated. So I'm here to talk to you about like a different way of designing these transport layer protocols. And the idea is we shouldn't just keep making new protocols as the lower layers evolve. Instead, we should sort of automate the process. We should have computer designed protocols so that if we can state a model of the lower layers and what we think about them, and we can state some mission or some objective that the application wants achieved, the transport layer can become just a function of that model and the mission. So that's what I'm here to talk about. And that's sort of the idea, these computer-generated designs. So my colleagues and I have done sort of a few different projects along these lines. We've made a transport protocol for cellular networks, for interactive traffic like Skype over a cellular network that I'm going to tell you about called Sprout. And then we've generalized that to the sort of classical multi-agent congestion control problem, when you have multiple computers all trying to share a bottleneck resource. So I'll tell you about those. We've also worked on this MOSH mobile shell program, which is sort of like SSH, but for today's sort of mobile internet, which I'm not going to talk about. And I'll talk very briefly about how we're extending these ideas to video streaming. But the general idea here is that all four of these projects have the same sort of structure, where the model of the lower layers and the mission that the protocol is trying to achieve are all sort of spelled out formally. And the behavior of the application of the protocol is in some sense just a function of the model and the mission. So that's sort of the commonality of these contributions. So let me go through and tell you about the Sprout. The main sort of idea here of all these projects that I want you to have, and I'll come back to this at the end, is that showing our work as designers produces dividends. So when I design a system, that's all well and good, but if we can show our work so clearly that a computer can retrace our steps, we get all sorts of cool results out of that. And that later, maybe the requirements will change, and we can retrace the steps a little bit differently, and maybe we get a little bit different system, and we can sort of explore the curve of what's possible and what's sort of entailed by changing requirements. That's sort of the main takeaway of this talk. So talking about Sprout here, this is a very concrete thing. This is motivated by a very particular observation about video conferencing over cellular networks. The observation is that if your advisor is trying to meet with you, but he had to go home at the end of the day to see his kids, so he's driving down the street in Boston, and he's holding up his smartphone trying to video conference with you while driving in the car, that really doesn't work very well. Has anyone tried this? Has anyone tried to do a video conference over a cellular network? Or Skype over a cellular network? Yeah, did it work well? No, not really. All right. So we see it doesn't really work well when the advisor is trying to video conference with the student while driving down the street, and the question is why? So we think that one of the major reasons is that these new cellular networks, yes, sir? Yeah, so he's really not even moving. He's barely even moving. Should work. So we think that one of the reasons is that these cellular networks differ in a few important respects from the sort of classical internet of 20 years ago that Skype in effect was designed for. One of the ways in which the cellular networks differ is that the link speed or the capacity as seen by an endpoint varies rapidly with time. So this is 90 seconds of data from the Verizon LTE network in Boston. And we can see the link speed varies very dramatically. It goes up to more than 1.5 megabits per second and then down actually to 0 and up again. So that's one difference. A second difference is that these cellular networks are very reliable. They're run by the phone company. The phone companies hate to drop a packet. So instead, we see very long delays as packets queue up in a standing queue or are retransmitted in the link layer to make sure they arrive reliably. So we see even 3 seconds, even 10-second delays during a TCP download. Yes, sir?
So this data is over a stationary point or moving point?
This data here is totally stationary. The previous graph, this one, is driving around Boston at rush hour. So these are sort of two differences, is that the networks are very variable in their speed and they're very reliable. So we think that that's the reason. That's sort of our explanation. But we wanted to test this rigorously. So we drove around Boston at rush hour. We sat on the bridges of Boston at rush hour. And we collected data from 4 commercial cellular networks, 2 LTE networks and 2 3G networks. And we flooded the uplink and the downlink of the phone to measure when packets actually transited the link. And we didn't just flood them, but we had to flood in a careful way so that Verizon wouldn't get mad at us and ban us. But we measured, making sure that the link was always backlogged, when packets could actually get through. We recorded that as a trace. And then we went back and put the trace in a physical hardware box that has 2 Ethernet cards that emulates the same cellular network with its varying capacity. And we ran the real versions of Skype and Google Hangout and Apple FaceTime over that variable network. So I'm going to show you now the results from the sort of red combination here. I'll just show you Skype running over the Verizon LTE network. So what we see in the top graph here is the actual throughput. The black line represents the actual capacity of the network, the same graph that I showed you before. And the red line is what Skype was sending. So you can see Skype is being pretty conservative here. It's not really using the full capacity of the network. Even when the network is good, Skype is not using it. And yet, look at what happens here about a minute into the trace. What's going on? So the network here deteriorated. The black line went down. And the red line, which represents the speed that Skype is sending, it also goes down, but not as fast. The red line sort of infringes on the black line. And this bottom graph here represents the delay, or the standing queue, that Skype builds up in the network as a result of that. So we see, in fact, because Skype is putting packets into the queue faster than they're being drained, it ends up building up a huge delay, like a 4-second delay, that lasts for almost 9 seconds. Has anyone had this happen when you're using Skype? Everything's great, and then suddenly you can't hear anything for like 9 seconds. Yeah, so this is pretty common, and we think that this captures exactly what's happening. When the network deteriorates, Skype ends up building up a standing queue. So if we had to summarize the performance of Skype and its competitors, we like to do it on one of these throughput versus delay graphs. So the better throughput is at the top of this graph, and the smaller delays, the better delays, are at the right side, because we flipped the x-axis here. So the best algorithms on this graph will be in the upper right, and Skype is not. Skype is getting a large delay. It's like a 1-second delay, which it's hard to have a conversation with a 1-second delay, and the throughput is not so hot either. And FaceTime and Google Hangout are broadly similar in their performance. Google Hangout does a lot better on delay, but the throughput's even worse. So, we think the problem is here, and we can measure this by sort of stimulating Skype and seeing what happens. All of these applications are reactive to the idea of congestion. The idea is that the video coder is going to encode video at a particular rate, and they're not going to deviate from that path until there's sort of conclusive evidence that something's going wrong, evidence of congestion, like an increase in the round trip time or packet loss. But the problem is, by the time you get that evidence, at least to be sure, it's just too late. You wait until you see packet loss, and then you reduce the rate. As we see with Skype, it's too late. By the time you get the evidence, you've already built up a standing queue. So we really think that this self-inflicted queuing delay is the main culprit in this problem of video streaming over a cellular network. So the question is then, can we do better? Can we make a protocol that is an explicit function of some assumptions about the cellular network that include these characteristics, the variable link speed and the reliability? That's the model. And some sort of mission that expresses what we think the video conferencing application wants. Can we do better? So we set out to try and do that. We made a protocol called Sprout. And this is the mission. The mission of this protocol is to get the best throughput possible on behalf of the video conferencing application. But more important than that, we want to bound the risk of building up a delay of more than 1/10 of a second. So the number one requirement is to try and make sure we don't build up a standing queue that's going to take more than 1/10 of a second to drain. Because that's what we sort of think characterizes an interactive conversation, 1/10 of a second. And subject to that requirement, get the most throughput possible. So that's the mission of Sprout. And what do I mean by this bounded risk of delay? There's sort of a 4-port process here that I'll tell you about. We actually model explicitly that variation in link speed that I showed you earlier. And then given the model, at runtime, we just do Bayesian inference to infer the current speed of the model. And then the receiver makes a prediction going forward by evolving the model about what the speed will be in the future, sends that prediction back to the sender, and the sender has a control strategy that's just sort of dictated by the output of the prediction about sending it as good quality frame of video as possible, subject to the requirement to bound the risk of building up a more than 100 millisecond delay. So I'm going to tell you about all those 4 parts in turn, the modeling, the inference, the prediction, and the control. Yes, sir?
The two ends of the communication might cross the country, in which case the simple round trip time is going to be greater than 100 milliseconds. So how to be able to bound the delay to be within 100 milliseconds?
Oh yeah, so the question is, how do you bound the end-to-end delay to be less than 100 milliseconds? Yeah, so we don't do that. We're just trying to bound the part that we control, the standing queue in the network. We try and bound the standing queue to be less than 100 milliseconds. But the sort of propagation delay is not something we try to control. All right, so the modeling, we're not exactly sure how to model these networks. We don't know exactly how Verizon decides who should get a packet when, and we don't know when the user's driving around, where the trees are, and what controls the signal-to-noise ratio. But we can observe the empirical impact on the endpoint. So one thing we look at, if you flood a phone with packets, again, this is a stationary phone, we can look at the distribution of inter-arrival times between pairs of packets. And if you look at this, you see this pretty heavy-tailed distribution here. It's actually very heavy-tailed. There's, the most common inter-arrival time is like 1 millisecond, but you see as big as almost 4,000 milliseconds. If you take this distribution to our electrical engineering colleagues, they say, golly, that looks a lot like a flicker noise process or a 1/f noise process. And if you do a fit to that, you see it's a pretty good fit. So that's in the sort of inter-arrival time domain. And if you look in the time domain at the sort of average packet delivery rate, I've shown you this graph earlier, you see again this variation in rate. And we say, golly, that looks a lot like a random walk or like Brownian motion. So these are two observations. And we built a model that was consistent with those observations. A model of the way packets are delivered over a cellular network. The model is the sender introduces packets to the back of a queue. The queue is drained according to some Poisson process, and the rate of the Poisson process is varied according to a random walk or Brownian motion. So this is called a Cox process. And you might ask, and so the model here, the model is that it's a generalized arrival queue where we control the arrival rate and a Markovian departure process, and this is the Markovian process. So you might ask, is this model true? Is this the way that packets are delivered on a Verizon or an AT&T network? And the answer is no. The model it's wrong. It's definitely not true. But that's sort of all models are wrong. But it's sort of okay. I mean, it still helps to have one. That's sort of the philosophy of this work. This is not. We're not saying this is the model of Verizon, but it is definitely the model of what our software does. And then we can measure how well the software does when the model is maybe not exactly perfect. And we can look at the sensitivity of the performance to the model. So that's the modeling. Yes, sir.
Do you have some intuition about the real-world situations that would cause the model to be most wrong? And so one that comes to mind is, this model would probably not be good at the Super Bowl. Right? A lot of correlated accesses that will make the throughput probably not be right. But I'm wondering, you've now got to monitor a bunch of different things. Are there situations where events happen or whatever that cause there to be correlation in things that were much more pure stochastic processes before?
Yeah, I think the situation where sort of most wrong is maybe in the best case. Like if you leave your phone sitting on the roof of the building and it has clear line of sight to the cell tower and it's 4 in the morning, the network is actually less variable than the sort of fixed volatility that we're assuming. So the predictions made by our model will be sort of too conservative in that case. And you can imagine if you're alternately dunking the phone in the ocean and not, then we might be too aggressive. So this sort of assumption of fixed volatility Brownian motion is probably our
those probably are real world things you have to worry about, either the rooftop or the dunking in water.
That's true. Oh, so the real world worst case. No, it's probably if you have a great if you're just sitting there right by the window and you have a great connection to the cell tower, we might be too conservative. I'd say that's probably the worst case for us. All right, so that's the modeling. On to the inference. It's really very simple. Bayes' theorem really dictates what we do. We observe the number of packets that come in every so often, sort of as fast as we can afford to integrate, and then we just update our probability distribution on that lambda, the rate of the Poisson departures from the queue. That's the inference. And the prediction is even simpler. We just take the current probability distribution on that lambda, and we evolve it forward according to the model in the absence of observation. So if we have a fuzzy estimate of lambda now, it just gets fuzzier in the future. And then we plot the 5th percentile. We make a conservative forecast of the number of packets we think will be delivered in the near future. It's the receiver doing that, and that looks like a curve of the cumulative deliveries that it expects in the near future. And that curve is sent from the receiver to the sender, and it looks like this. This is the prediction. And then the control strategy is just a function of that prediction. The sender looks out 100 milliseconds in the future, and it sends exactly that many packets. And as time progresses, we can look out 100 milliseconds next time, and we can send more packets. 100 milliseconds, we can send more packets. So the actual behavior of the sender is purely a function of the model and the mission. So the question is, how well does it work in practice? So let's look at the same. Oh, yes, sir. Sure.
So the first one.
Yeah.
But isn't this cautious forecast being updated continuously?
Well, yes. So the receiver sends a new cautious forecast to the sender whenever it can. But sometimes there's intervals when the sender doesn't have a new forecast. And in that case, it just uses the out-of-date forecast. But you're right. So eventually, this will be replaced with a new curve. Yes, exactly.
So that's during the time that it hasn't received it updated.
So let's look at how well this does. On the same trace that I showed you earlier, I've just added one line, the blue line, which is the Sprout algorithm. So we see as the capacity varies, Sprout is actually able to claim more of the available capacity of the network than Skype is. So you can see here where it got really good, Sprout was able to ramp up its throughput and provide that to the video application. Now maybe the video application doesn't want to use it, but we at least make it available. But what happens here where the network gets bad? We can see here the black line went down. If you recall, the red line sort of infringed on the black line, and Skype was sending more than the network could take. But Sprout doesn't do that. Sprout is able to, to keep the blue line below the black line. Now, it's not clairvoyant, but what's different here is that Sprout is not waiting for conclusive evidence of congestion. Sprout is really trying to forecast conservatively how many packets can be delivered in the near future and make sure it doesn't send more than that. So Sprout is able to ramp down the rate as the real rate ramps down, and where Skype builds up this large delay, Sprout doesn't do that. Now maybe Sprout is sending terrible quality video here, or maybe even no video at all. Maybe it's only audio. But Sprout is very opinionated. It has a mission, and the mission says much better to have audio with less than 1/10 of a second delay than great quality video with a 4-second delay. That's the mission of Sprout. Yes?
Is that end-to-end delay in the bottom or just queuing delay? I don't understand why you have any queuing delay if you're always sending slower than the capacity.
Okay, well, so first of all, yes, we are seeing end-to-end delay on this plot. But also, the packet arrivals, I mean, this is a real trace of packet delivery. So there can be intervals where there's no packets delivered, and during that time, they'll just accumulate.
So this really burstiness is what we're looking at on the bottom.
Yes.
The blue on the bottom is about burstiness.
Yes. Yeah, so and there's some more technical points here that we could talk about offline. So, I mean, this is really where we think the win of Sprout comes from, is being able to sort of forecast congestion before it happens. So on this, yes, sir?
So if the model is maybe wrong, why not choose a much simpler model which just says that if I look at the derivative of my bandwidth over the last period and I just project forward that for the next, the next little bit, and skip all the complications that you've
Yeah,
got?
so that's a great question. If you'll bear with me for about 4 slides, I hope to knock that one out of the park. Actually, I won't be the one knocking it out of the park. I'll show you why I think I have an answer for that in about 4 slides. That's a great question. Actually, in the paper, we do study exactly the strategy you're talking about. And it actually works great, which is why I don't think we're very sensitive to the model being right or wrong. It turns out it doesn't really matter. But if we plot the performance here of these schemes, these were the video conferencing schemes. We also looked at sort of delay-sensitive TCP congestion control schemes. And we also looked at the default TCP congestion control scheme in Linux, which is Cubic, which is over here. So Cubic really cares about throughput. It gets awesome throughput, but terrible delay. So this is the default in Linux. And this one, Compound TCP, is the default in Windows Server. And whereas Sprout on this graph, it's there. So it doesn't quite get the throughput of TCP Cubic, but it gets much better delay than anybody else with this strategy. So this is on the Verizon LTE downlink. And if we look at the uplink of the same network, a similar story here, where Sprout is getting the minimum delay, but not quite the best possible throughput. We also tested these 3 other links, the AT&T and the T-Mobile. And if you average across all 8 links that we tested, you see on average compared with Skype, for example, Sprout is getting more than twice the throughput. But more important than that, it's reducing the delay by almost a factor of 8. This is sort of the bottom line win of the Sprout approach. It's not a universal win. For example, compared with Cubic, it's 9% less throughput, but it reduces the delay by a factor of almost 80. So there's a trade-off. So one other thing we looked at is people say the problem here is not Skype. Skype is fine. The fault really lies with the phone company. And so the fact these packets are allowed to accumulate for 10 seconds in the Verizon base station on the downlink, and they're allowed to accumulate for actually even longer than 10 seconds in the Qualcomm baseband chip on the phone for the uplink, that's really the problem. And what we should really do to fix this is persuade Qualcomm and Verizon to install some sort of active queue management so they don't hold on to packets for 10 seconds. There's a buffer bloat community that proposes these kinds of solutions, and we found that in fact they're right. If you take TCP Cubic, for example, over a cellular network, and you instead, if we got Verizon and Qualcomm to install an active queue management scheme, it would dramatically improve the performance. It would dramatically reduce the delay. But in practice, you can actually get similar results by changing only the endpoint and running over the original cellular network. So I don't have a sort of ideological view about whether end-to-end or in-network is better. It's a total lie. I do have an ideological view, but that's not the point of this talk. The real message is that we can actually compare these empirically. We'd say, okay, end-to-end solutions or in-network solutions can give comparable results. And then, the decision about which one to do is a question about deployability or some higher level concern. So, this naturally leads to the question, and you asked it, sir, what if you change the model, or, are you sensitive to the model? Can you do even better? So, one approach would be for, my colleagues and I, Anirudh and I, to try and do better, but actually we had an even better idea, which was to make this a contest for our advisor's students in his graduate networking class. So I'm not allowed to call it a study, but we did a contest for a few weeks in the class. We went in and we said, all right, guys, we have taken our evaluation procedure, and actually it's now in Ubuntu Linux. So if you want, you can apt-get install our evaluation tool, and you can run it, and then you can run any congestion-controlled protocol you want over the same Verizon trace and the same network, and you can measure how it is compared with Sprout and TCP and anything. And we said, all right, your mission is to maximize throughput divided by delay, and we'll give prizes for the 4th and 3rd and 2nd place, and if you actually beat Sprout on this metric, we'll give you the absolute most grand prize, which is to co-author a paper with me and Anirudh in a future networking venue. And there was sort of like a big silence when we announced this very proudly, and one guy finally raises his hand. He says, well, what if we just want more money? But actually, we insisted on this, and some students did very well in the contest, and we've actually just submitted the paper. So this is what we gave the students at the beginning of the contest. We said, all right, here's on the same Verizon LTE trace. If you had complete foreknowledge, this is how well you would do. If you knew every squiggle, every change in capacity the network was going to do, here's how well Sprout does, and here's how well Skype does. And we gave the students a leaderboard so they could see dynamically who was doing how well, and there were some machine learning grad students in this class. They were very competitive. They did all kinds of crazy things with boosted, random, crazy things. And so the students, there were 40 students in the class, and they made 3,000 attempts. And here's sort of all 3,000. So what I like about this graph is that it suggests there really is a sort of achievability region of this problem. And if you draw the convex hull, there is a sort of efficient frontier of the best, the family of best algorithms. And there's not one best algorithm. The application might choose to be here, or maybe it will choose to be here. And Sprout is very near this frontier that the students discovered. But we can't say that Sprout is the best because it depends on your mission. And the students who actually did very well on this throughput divided by delay metric, who were right here sort of in the knee of the curve, they actually had a really, really, really simple model, which was, just like you said, extrapolate the rate over the near future and actually increase that estimate by 5%, and that's what you do. And these students did great with the same sort of a packet accounting approach that we have. So it turns out it's not particularly sensitive, the exact model you use. And the nice thing about this is when someone else comes up with a new scheme, as I know there's some papers coming out that compare with Sprout, they're going to say, well, here's where we are, here's where we are. Maybe someday someone will be here. I can't tell you for sure whether that point is achievable or not because it's, 40 MIT students may or may not be an oracle for this problem. But it suggests that there really is a sort of achievability region. And it's fun to sort of look at that. Yes, sir?
So my question is, look, these are the results on one side of the trace. I was curious if they take the same algorithm, run a different set of trace, get the same line.
Yeah, so for the real contest, we made everyone send us the Git hash of their final program. And then we had the undergraduates drive around and collect new data from Boston. And we brought the new data back, and we ran everyone's program on the new data, including Sprout. And that's how we decided who the contest winners were. And actually, the most aggressive machine learning graduate students, we made an animation of where they were on the training data and then the test data. And the machine learning grad students actually had the worst training to testing correlation.
But if you take the ones who weren't kind of the anomalies, the good algorithms, aside from the good algorithms in one data set lead to good algorithms in the other, or in fact, do they?
It's about 50-50. 50% of them, and empirically the ones who were the simplest in their design sort of retained their performance. And the ones where, and it's not like we only gave them one sample. We gave them multiple cellular data sets to train against. But the ones who were sort of the most aggressive did sort of the worst when it went to the testing data. Oh, yes, sir?
Anything not from Sprint?
Oh, I'm sorry?
Is it all Sprint? Or?
No, so we gave them some Verizon, some AT&T, some T-Mobile. But all in Boston. All right. So there's been some commercial interest in this, and we're actually working with some startup companies to put the code of Sprout into their video conferencing products, and with some bigger players to put sort of the ideas of Sprout, or this idea of packet accounting and predicting the delay into their products. So, I can now say that Sprout has had a dramatic effect on this sort of tableau of congestion control. That's sort of my contribution. So, you know, Sprout is a particular algorithm that sort of solves one problem, but it has some important limitations. And one of them is about the domain of the problem. Sprout solves this problem of a cellular network, where there really is a queue that my sender, my cell phone, is introducing the packets to the back of that queue, and that's the queue for my cell phone on the base station. And it goes over this variable link, and it goes to the receiver, and I get those acknowledgments. That problem does describe the cellular network. But the classical problem of congestion control is not like this. In general, the problem that people have worked on for 30 years, there may or may not be some second guy who may or may not be introducing packets to the back of the same queue. In fact, there can be any number of senders introducing packets to the same bottleneck. So this is sort of the classical problem. So the question is then, you know, can we expand Sprout? Can we generalize it to this multi-agent congestion control problem, where we really want to make an algorithm, just like TCP New Reno or TCP Cubic, that handles multiple computers contending for the same bottleneck? So that's what we went to work on. There's been a ton of prior work on this problem, which you know, I didn't have enough space on this slide to show a million papers. So, but in the late 80s is when Jacobson proposed this sort of additive increase, multiplicative decrease algorithm for TCP that we still use today. It wasn't for 10 years after that that the theorists started to be able to answer, you know, what is the problem for which TCP is the solution, or what Damon Wischik calls the teleology of TCP. What are the ends for which TCP is the means? Kelly and colleagues started to solve that problem in the late 90s, where they were able to formulate an optimization problem that in the asymptote, as you know, if downloads last forever, TCP maximizes an objective function. And it wasn't for 10 years after that that a different group of theorists started to talk about some results in the regime where downloads don't last forever, this sort of stochastic network utility maximization problem, where we can describe the existence of some stable algorithms in that regime. Although, yeah, anyway, we can describe the existence of some stable algorithms in that regime. So we tried to sort of solve this problem constructively and actually come up with algorithms that would try and maximize some measure of performance for this problem. And the basic question that any congestion control algorithm has to answer in this framework is basically just, do I send a packet or do I not send a packet at any given time? So we're not talking about how big the packet should be. We're not talking about what route the packet should take through the network. We're not talking about what bit should I set in the packet. We're just talking about, do I send one now or not send one now? This is sort of only actuation that we're going to explore. And this decision is made given everything that the computer has observed so far. So every packet it's already sent out and every acknowledgement that it's ever received. That's the sort of information it gets to use to make this decision. It's still a really hard problem. So we make it a little simpler by adding another footnote, and to say, to start out, we're going to make this sort of super rational assumption. And we say, let's assume that every node is running the same algorithm. You know, we're the protocol designer. We're going to design a new algorithm. Let's assume every node is going to run that algorithm, and then let's try and find whatever the best algorithm is. So that's the super rational congestion control problem. And this was a framework that Douglas Hofstadter first formulated in Scientific American. So, you know, I talked about this with some of my theorist colleagues, some of the robotics and planning people, and they got very excited. They say, you know, I think this problem is a decentralized, partially observable Markov decision process. They got super excited, and indeed, I went home and I worked it out, and it is. You know, the independent agents are the endpoint computers, and the state of the system is what packets are currently in the network, and the actions available to each sender is, you know, send a packet or don't send a packet, and the observation is those acknowledgments, and we have the model and the mission like we talked about, and it's impossible. You know, it's like doubly exponential. It's nx pard. So unfortunately, just because you sort of know the name of the problem theoretically doesn't mean that you can solve it. And for this reason, I suspect that the theorists will never actually be able to give us a conclusive solution to this problem. I think it may be too hard. Now, I haven't proven that because I don't know that the particular problem of congestion control is as difficult as the general decentralized POMDP. But I suspect that we may never have a theoretical solution. But we can provide existence proof, so we can demonstrate sort of inner bounds that some results are achievable. So that's sort of what I do. And we created a program, REMI, which is it's a computer program that generates these congestion control protocols in order to satisfy some objective, some mission, and given the protocol designer's model or assumptions of those lower layers. So the protocol designer specifies their assumptions of the lower layers of what prior knowledge the protocol is entitled to have, and some mission that the protocol is supposed to achieve on behalf of the application. And then this program thinks for a few hours or a few days. That's on an 80-core machine that I stole from our systems colleagues at MIT. I mean, the CPU time. So it thinks for a sort of a CPU year, and the output is a congestion control protocol, what we call a REMI-CC, a REMI-generated congestion control protocol. So I'll tell you how we do that. Encoding the model requires the designer to sort of formalize what do we know, or what are we allowing the protocol to know about the network. So this could be a very broad model if it's for the internet, or we might have very specific information if it's for a data center about the parameters of the network, and also some model of the workload, web browsing traffic or MapReduce or something like that. And the objective function, or the mission, also we have to be clear about. What is the goal of congestion control? Some people have proposed this idea that we should maximize the proportionately fair throughput, the sum of the log of the throughput of each individual sender. That's one approach. The function I'm going to talk about mostly in this talk is about proportionally fair. We want to reward throughput but penalize delay. So we want more throughput for a particular node on the network, but you also want to penalize end-to-end delay. Like if you're Skype. This is called the proportionally fair power. And one thing we can do, we can take this delay term and we can sort of change how important we think it is. We can add this sort of delta parameter to express some series of trade-offs between throughput and delay. So this is the objective I'm going to talk about, but there's actually tons of possible goals of congestion control, or really of distributed resource allocation that we could discuss. Maybe we want to avoid certain pathological events, or maybe we care about energy consumption. REMI, the program, is agnostic as to what the appropriate goal is, as long as you, the protocol designer, can sort of express it. All right, so that was the model and the mission. But the problem is still really hard, because if you have to make a decision about sending or not sending a packet at any moment in time, given all the information you've collected, that's a big space, because all the information you've collected is like really big. It's like at every moment you got an acknowledgement you didn't. So instead, we're going to dumb this problem down further. We're going to summarize the history with a series of just features that are summary statistics of the history. So in fact, we in practice use just 4 features. We have a moving average of how fast acknowledgements are currently arriving. And we have a moving average of how fast packets are going out. We're sending packets. And we have a ratio of the most recent delay to the smallest delay so far. So instead of the whole history of everything that's ever happened, the algorithm is only going to consider these sort of 4 real numbers. So that's the features. And you could ask, why these 4 features? And the answer is really, we can make this decision empirically. If you give me a new feature that you suggest would help, like explicit congestion notification or anything, we can put that into the optimizer and we can measure the quality of the resulting algorithm, and we can see how much it helps. And with the existing features that we have, we do a sort of knockout mouse experiment where we dumb down the algorithm by removing one of those features, and we rerun the optimizer, and we see how much it hurts to not have that sort of sense available. So we can answer sort of empirically, what is the value of having more information about the network? So the job of the REMI-CC, the algorithm at runtime, is just to map that 4-dimensional input space to some action. What are we going to do when we're in that situation? And the action for us is going to be just like TCP. There's going to be a congestion window, sort of the number of packets that can be in flight at any given time. So the action is a multiplier to that number, an increment to the number, and then some minimum interval between 2 outgoing packets, or a pacing rate. So these algorithms at runtime, they can be window-based or they can be rate-based. And in fact, we see empirically they switch between those behaviors on a sort of fast time scale. So yes, sir?
And they're run independently on each node?
Yes, that's correct. Yeah, they're run independently on each node. So the algorithm at runtime is a mapping, and then the runtime behavior is just when it gets an acknowledgement, it updates the congestion window, just mx plus b, and it sends a packet if the window is big enough and then the last packet was sent long enough ago. So I'm going to show you quickly how this optimization runs. The job of the optimizer program, the REMI program, is just to find the best mapping, the best REMI-CC between those input 4 numbers and those output 3 numbers. So we're looking for a mapping between 4 input dimensions and 3 output dimensions. Unfortunately, it's hard for me to show those 4 input dimensions on this projector. So instead, I'm going to kill 2 of them just for this demonstration. I'll just show you a 2-dimensional input space. All right? And I said we had to be clear about the model and the mission. So here's the model I'm going to use for this optimizer example, which is that the link speed and the round trip time and the number of senders are chosen from some uniform distribution. And the mission is going to be just like we talked about, this reward throughput, penalize delay. And now let's look at the mapping that results. So we're going to look at this mapping. The input to the mapping are those 2 congestion signals, those 2 features, which in this case is how fast are we sending and how fast are we receiving. And the output to the mapping is going to be this action that we talked about, the multiplier, the increment, and the pacing rate. So when we start out, we don't know what the answer is going to be. And we just look. At the beginning, we do sort of gradient ascent or hill climbing to find the single best action. So this ends up being the answer. So I can sit here in La Jolla and tell you, by golly, if you always have to do the exact same thing in response to every acknowledgement, then you better deduct 10% from the congestion window, add 4 packets to it, and make sure you have 3 milliseconds in between every pair of outgoing packets. That's the best congestion control algorithm. It's a little silly to always do the same thing. I mean, ideally, we'd want the action to be a function of the congestion signals. Otherwise, sort of what is the point of collecting those signals? So we really want to divide up this mapping so that the action depends on where we are in this sort of state space. So we're going to split the mapping here so that half the time the state is to the left of the split. And we'll split it in every dimension. So half the time the map is on either side of the split. So when we split, it looks like this. We end up with now 4 different rules. And we can simulate and see where the state ends up being. And the sort of darker red is where we spend most of our time. And we can see, indeed, about half the time it's to the left of the split, and half the time it's to the above the split. And in fact, we're spending most of our time on this y equals x diagonal, where the send rate is similar to the receive rate, which is really what you want. You don't want to be sending a lot faster or a lot slower than packets are being received. If you're sending fast, you're probably building them up in a queue. If you're sending slower, you're probably wasting. So then we really just recursively repeat this process, where we just keep dividing up the most popular rule and then optimize when we do gradient ascent on all the different rules. So we just do that over and over again, and that's why it takes a year, a CPU year. And we end up with a very complicated mapping between these input variables and then this output action, with most of the attention of the optimizer focused on this y equals x diagonal, because that's where we're spending most of our time at runtime. All right, any questions on this optimization procedure before I move on to the fun results? No, OK, great. OK, so this is how we get this very complicated mapping. Of course, in real life, it's even more complicated because we have 4 input variables. So we evaluated, oh, yes, sir. Yeah.
So it seems like there's some pretty sharp discontinuity.
Yes.
That could lead to bad performance.
Yes. Yes. So let me look at this in just about 1 second. So there's these sharp continuities. We end up with these very high gain bang bang controllers, which I'll show you what ends up happening. But yeah.
Because just going from the top to the bottom, first you're going to wait for 5 milliseconds in between packets, and then all of a sudden 40 milliseconds.
Yes. The trick, first of all, is that it's hard to tell in any given box whether we're governed by the windowing or by the pacing at any given time. So when we're opening up the window, the pacing ends up taking control. But this negative 256 here is now trying to shut down the window. So the pacing probably doesn't, my guess would be that when we're in this box, which as you can see is pretty rare based on how dark it is, the pacing probably doesn't have almost any effect because if we shut the window. So it really is, the behavior of these is, wandering around the state space at runtime is quite complicated. Why don't we just look at it? So here we have a little simulation. Oops, core dumped. OK, let's try this again. Here we have a little simulation looking at the behavior in runtime. And here's time evolving. And what we have on the y-axis is the number of packets in flight from any given algorithm. And the black line here represents the ideal number of packets in flight, the bandwidth delay product. So if the number of packets in flight is less than that, that's bad because a scheme is not using the link enough. It needs to get at least to the bandwidth delay product to be using all the capacity that's there. But if the number of packets in flight is a lot more than that bandwidth delay product, that's bad too, because that means we're building up a large standing queue. So let's set up a scenario here. We can change the sort of link speed. How fast should we go today? Let's go like 10 megabits per second. So you can see that changes the bandwidth delay product. We should also change the buffer size here, the sort of queue length that's permissible inside the network, because it turns out TCP is very sensitive to that. Let's make it, I don't know, 1,500 kilobytes. All right, so now if we start up an old-fashioned sort of additive increase, multiple decrease TCP, let's look what happens. So we'll start it now. We go through this slow start algorithm, and then the number of packets, holy cow, keeps increasing until we hit that buffer. This blue line is the maximum capacity of the queue in the network. And now that we've had buffer overflow, TCP goes into this additive increase phase here, where the window is increasing by 1 every round trip time. So if we now start a second TCP, I'll start one now, we go through this slow start process, and you can see it's quite slow here, starting up, this sort of purple TCP. It's slow because the first TCP has put way too many packets in the network. So the sort of effective round trip time is very large. So now we get into this sort of quasi-equilibrium here, where the network is saturated. Both of these TCPs have more packets in the network than they should. They both have more packets in flight than the bandwidth delay product, but less than that buffer size. And so we have this sort of persistent unfairness, where the purple line is sort of persistently over the red line. Now, how can this be? Kelly et al. Proved that TCP is asymptotically fair. Well, the fact is the asymptote can take a long time to get to. So if we speed up the simulation, we'll see the purple line is ahead of the red line, but they keep additively increasing here, and eventually we'll have the TCP sawtooth, where they have a multiplicative decrease in their window. And if we do this long enough, we see still this persistent unfairness. Eventually, there we go. Well, competitor needs to be low. Okay, there we go. So eventually, almost maybe 45 minutes in, they've converged to sort of a fair allocation of the throughput. So that's sort of the status quo. When the signal that TCP uses is this buffer overflow induced packet loss. So I see well, anyway, okay. So let's turn off the TCPs. And now let's turn on one of these REMI optimized congestion control algorithms. This was optimized for between 3 and 300 megabits per second. So that was the model, is that the link speed is over that 100-fold range. And if we'll zoom in here, we'll zoom in. When we turn on the REMI designed congestion control protocol, here's what happens. So we go through this sort of fast start, I don't know what you call it, and then we end up in a sort of loop here, a limit cycle through the state space with this very high gain controller, as Jeff pointed out, where the number of packets in flight oscillates close to the ideal number. And if I start up a second REMI design controller right now, very quickly they start to share the link. So instead of that sort of long convergence time, the convergence time is much faster. But you see the behavior, it's better. They're sharing the link almost immediately. But we get this very sharp or high gain behavior. And if you look at what's happening in the state space, they're going over those very sharp edges that we saw. It's sort of like a thermostat turning on and off rapidly. So the behavior of these things at runtime is essentially this sequence of these high gain bang-bang controllers. So we evaluated this quantitatively in NS2, and we compared against Neurino and Cubic and these other end-to-end congestion control schemes. And we published our setup here for replication. So you can go to our page, and you can click the blue reproduce the results button, and you can get the sort of same graphs that I'm about to show you. The setup is, as I showed you, with this sort of dumbbell network with multiple senders going into a queue here. The model is the same as I showed you before. And let's look at a simple case that is consistent with this sort of training scenario. So the model, for example, what we've told the optimizer is that the number of senders is going to be drawn uniformly between 1 and 16 competing senders. And let's look at when the actual number of senders is 8. That's the model. And for the mission, it's this reward throughput penalized delay. And we're going to look at 3 different importances for how important delay is relative to throughput. So looking on one of these throughput versus delay graphs, the results from sort of a standard TCP Neurino with 8 senders look like this. We get sort of 8 dots. And if we run it lots of times, we get lots of dots. And we can summarize these with sort of the median and a 1 sigma ellipse that sort of shows the range of variation. If we look at what that ellipse means, sort of how tall it is how variable are the results from TCP Neurino in the throughput axis, or how unfair is it? And sort of horizontally, how unfair is it in the axis of delay? So that's TCP Neurino. I'm going to take away the individual dots now, and we'll just look at that ellipse. If we look at all the TCP schemes, like Linux's Cubic and Vegas, we can see there's a sort of continuum between whether they care about throughput or about delay. We also looked at schemes that put the smarts inside the network, like XCP and fair queuing and CODL. So if you run over those schemes, you actually get much more consistent behavior, and you get better throughput. So this is TCP Cubic running over fair queuing and CODL, and this is XCP, which runs at both places. You actually do better if you can put the intelligence inside the network, at least on throughput. And where were those 3 computer-optimized schemes? They're over here. So there's a scheme that cares mostly about throughput, and that gets the best throughput, and a scheme that cares sort of a compromise, and one that cares mostly about delay. So we can actually connect and see sort of the sort of efficient frontier of the scenario, and in this particular one, it's dominated by the computer-optimized schemes. They're getting better throughput and better than delay, not just better than the other human-designed schemes, but even the best human-designed in-network control schemes. Just sort of a surprising and hopeful result. It suggests that end-to-end approaches are actually more powerful than we may have thought. But this is a scenario that we, in a sense, trained for. So we also looked at scenarios that were not consistent with what we trained for. And here's one looking at the Verizon LTE trace. We see it's not as good. The REMIs still largely dominate the efficient frontier, but they're much closer to the sort of human-designed status quo on this Verizon LTE trace. So now that oh yes?
Talk about a meta question. As someone who's done a bunch of papers in the space, and students go and look at traces and try to understand why the performance is the way it is. With these existing algorithms that have relatively simple control rules, 3 or 4 statements, it's still a huge nightmare to explain why you got bad performance on one particular run, and extracting that out takes a great deal of effort. Imagine Remy succeeds, and I have a thing that is, I don't know how many variables you have in this matrix, but a gazillion. Is it even vaguely debuggable when you have a congestion problem as to why and what you should do about it?
I think it depends. I think that's a hard question. And the argument that I'm going to make is that Remy really shifts where the complexity lies. So with TCP, we have, as you say, simple control rules at the endpoints. But the emergent behavior when you have a flock of machines running TCP can be very complicated and actually even chaotic. With Remy, we have these very complicated control rules that the computer designs at the endpoints. We saw that mapping. But the overall behavior ends up being more consistent. You can see there's less variability, less global bugs than when you have the simple algorithm. So the complexity sort of moves from instead of the emergent behavior being complicated, it's the control rules that end up being complicated. So, that's one answer, is that, the complexity is still there, it's just in a different place. We do now work on reverse engineering these algorithms, and we can sort of reason a little bit about why they work the way they do. We have the sequence of these high-gain bang-bang controllers. One thing you could look at is we can put into the mission, we can enforce a sort of comprehensibility rule. We can look at smoothing it out and see how that affects the performance. We've tried that, and it turns out making it a little bit comprehensible hurts the performance a lot. So this is the current answer. So there's some trade-offs here. The other thing we can do is to put in circuit breakers, and we can say, okay, well, at least we should be able to reason a little bit a priori that certain things should never happen, and enforce that either statically in the design phase or at runtime, make sure that certain things never happen. And in that sense, we can reason a little bit about edge cases. That's sort of the best answer I have. Yes, sir.
So about this way that this is kind of trained and then distributed, isn't it all possible to train it for the different end nodes independently, or at least in smaller groups, rather than for everybody, and then everybody has to do the same thing?
I'll show you. Let me show you a little bit on that question. So now that you have this protocol design tool, of course, it's very tempting to sort of ask all kinds of cool questions with it, because you can ask, really, if we change a problem like this, what happens, and what's the cost of backwards and forwards compatibility? There's all these cool questions that now you can have a computer answer. So we look, for example, at what is the cost of backwards compatibility. Like if the super rational problem is all well and good, but in real life, I'm not going to get everyone to change over to a new scheme on day one unless it's like in a data center that I control. So we look at, well, maybe we should make it backwards compatible. So here we see the performance when you don't need backwards compatibility, when you're in this homogeneous scenario. And we see TCP Neurino here is getting high delay. This is on a 10 megabit per second link. So it's sharing the link equally. It's getting 5 megabits per second, but it has high delay, and this sort of super rational computer design algorithm gets low delay. And what happens if we tell the optimizer, hey, it's not a super rational case. There's a 50% chance that you'll be contending against your own species. There's a 50% chance you'll be competing against TCP Neurino. So we design backwards compatibility into the algorithm. But then we run it in a case where you don't need the backwards compatibility. We run it only against itself. To do that actually makes the performance worse. There's a cost of this sort of backwards compatibility, this TCP friendliness. The algorithm ends up getting more aggressive and higher delays just because of the possibility of a TCP competitor. But then in the flip side, where you do need the backwards compatibility, if you don't have it, you're in bad shape. So this is what happens if you run the super rational computer design algorithm against TCP Neurino. That's a bad situation. Neurino is stealing more than 60% of the link, and our poor algorithm is getting less than 40%. It's getting squeezed out, and the delay is pretty bad in both cases. So what about the one that is designed to compete fairly against TCP? In that case, there's a huge benefit to that TCP awareness. If you use the TCP-aware computer design algorithm, they both get the fair share of throughput, and actually the delay is improved for both of them. And if you look at why that is, it's insane how it's happening. The computer design algorithm is actually learning to psych out TCP, where it'll very quickly fill up the queue, so TCP will back off, and then while it's backing off, it'll take its throughput. You get crazy behavior. It's like a dog training a rabbit or something like that. So now when we have these debates in systems design where you come up with a new protocol and you say, should it be backwards compatible or not, we can really evaluate sort of the cost and benefits of that. Let me skip over, actually. We also looked at the cost of forwards compatibility for designing for a broad region. It turns out, if you design for a very narrow region of of link speeds, you can do great in that region, but terribly outside of it. And there's a question about what if you build in breadth for future unforeseen scenarios, what is the cost of that? So you can design over a 10-fold range or 100-fold or 1,000-fold. And there's weak evidence that there is actually a cost to having more breadth of scenarios. But on the other hand, it is still possible to outperform TCP cubic and even cubic over this fair queuing over a broad range. So let me, just to summarize, as we talked about, I really think with ReMi, we move the complexity here. We had complexity in the behavior, and now we're going to have complexity at the endpoints. And which one is better or not is not maybe a question that I'm prepared to resolve. Briefly, I think the next step here is that almost any systems design problem, we should sort of think about, it's so much fun to design a system using your own intuition. You've been using a computer for however long, and you have all these ideas how the solution should work. But what if instead of writing down the solution, we really try and teach the computer to design the solution? And we make the answer that you think is the right answer just a point in the design space. So I'm working with my colleague now on this video streaming problem where Netflix and YouTube and Amazon Instant Streaming would be just points in that design space, points in the compromise between how much you care about quality and starting up quickly and not having stalls and being able to seek quickly. And if we can express our real preference for these things, or maybe even expose to the user and let them choose, do they want high quality that they're willing to wait for, or they just want to watch the cat swat the bird, immediately, some choice, then the program can actually then navigate through the path of the whole video in some sense the optimal fashion. So we have this sort of state passing style framework of video decoding that we use to make sort of any path, any quality level for any frame be an achievable path. So this is sort of one problem we want to work on. And then this problem of routing, what if, right now when you send a packet over the internet, you deliver your packet with a destination address to UCSD's network, and they give it to some company that, they have a legal agreement with, and they give it to some other company they have a legal agreement with, and, what if we can replace the lawyers with computers, making deals, and everyone just chooses the own route for their packet, in some computer design way? Can we make this work? It's another, if I had an answer, I would give you the answer. I don't know if we can make it work, but we should try to see if these sort of computer design schemes, can actually be possible. In general, I think almost any systems design problem, it's better to sort of show your work to the computer. If we can make the design considerations explicit, that actually gives us freedom to make changes. Just like we have a regression test for correctness, gives us the freedom to refactor. If you have a sort of regression test for design criterion, which could be performance or flexibility or whatever you can care about, if you can dream it, by expressing it rigorously, that gives you the freedom to make changes later. If the internet changes, or we have Wi-Fi that doesn't mass stochastic loss, we can change the assumptions and end up with a different transfer protocol and sort of map out the space. So that's sort of the vision of systems design that I want to impress upon you, is this idea of showing your work and asking, for any given system, if that's the answer, what's the question? So I've shown you Sprout, the transfer protocol that competes with Skype and Hangout and Google FaceTime over these cellular networks, and ReMi, which generalizes that to the sort of multi-agent classical problem. And we also talked about Alfalfa, which is this network video, again, that optimizes an objective just like Netflix and Amazon. And that's sort of where I think things are going, and I'd be honored to take your questions.
I'll ask one. So you made this distinction at one point between in-network versus end-to-end as a way of dealing with decisions. And many, when you started off, you talked about these assumptions that were kind of fuzzy. And a lot of the assumptions had to do with the fact that we really didn't know what was going on. So we assumed that reordering means that there's congestion because that's the fastest way we actually learn that the packet might have been lost, given the cycle queue. What about something that's both? So where you have the network tell you about the things that it knows, and then the end-to-end system, in fact, can be designed around having more knowledge and not being blind. Is there a reason to think that that won't be better than just an end-to-end design?
I think it will. No, I do think that getting more information from the network is probably helpful, and I think we can measure that now. We can say if we had explicit congestion notification, or if we had explicit rate notification.
Is it 10% or is it 100% more? How close are we to just end-to-end stuff?
I don't know. I mean, the initial purpose of this work is to say, okay, if TCP purely end-to-end is here, and XCP, which has cooperation from the routers, is here, how close can we get by optimizing TCP? And we were very surprised that instead it was better than the in-network schemes. So I think we now have to go back and say, okay, how good can we make the in-network schemes? I don't think we know that yet. Yeah.
Very well said. But you discussed a lot of your work was focused on the wide area network and the internet. But now, as we see, the latest trend is moving towards data center technology, and the trend in data centers is moving towards networks with the shallow buffers, and where the storage is less in the network. You have optical networks, you have all these proposals such as P-Fabric, which talk about really shallow buffers in the network. And the onus of all the buffering and everything is moving to the end host. So if you take these two worlds, can you come up with a unifying, so with this model that you've proposed, how hard or easy would it be to come up with a single unified model where you could just tweak parameters about the network and then come up with policies for the internet and just a unifying model for both? Would it be too hard, or should different practices be applied for the internet? And
I think we're very close to that, actually. In our paper, we compare against data center TCP, which is a sort of predecessor of P-Fabric. And we compare, data center TCP has a particular sort of in-network scheme, and we look at what if you try and do it purely end-to-end in a computer-designed way, and with REMI, and the results are sort of comparable. We weren't able to compare against P-Fabric, sort of because of the way our replication. Short story, we haven't yet been able to compare against P-Fabric, but I do think we're quite close to that idea, where you could express exactly what you know about the network. I should be clear. I think we're quite close to being able to express what we know about the network and design automatically an end-to-end control scheme. But schemes like P-Fabric also rely on particular policies executing inside the network. And I don't yet know how to parameterize those in a way that I would have confidence that I was actually searching the space of good policies. So if you wanted a computer to discover something like P-Fabric, where you have this notion of the 16-bit priority and you choose at the router, I don't know how to do that yet.
so my question was, so you do a very good job of abstracting what's there in the network. My concern was, what about the end host? What about the network stack at the end host? So you talk about transport, but then there's the software processing that's taking place in the end host. Do you take that into account as well? And that's again just another parameter that could be added to the model.
Yeah, I think that's part of the model, yeah. Yes, sir.
What about if you have a big network and you're replacing just 1% of the nodes with your method? Would that gain anything?
Well, so the only quantitative answer I can give you is this question where you look at 50% of the nodes. To replace 1% of the nodes, well, it would depend. If they're all sharing a single bottleneck and you have a delay goal, it's very hard for 1% of the nodes to have any sort of effect on the delay, because the delay is sort of dominated by the worst actor. So if the delay is already large because the other 99% of the nodes have built up a standing queue, it's very hard for any individual node to fix that in a sort of end-to-end fashion.
But let's say just you and I want to do Skype.
Yes.
And we both use your protocol rather than the other protocol.
Yes.
Would it help us?
Well, on a cellular network, absolutely, yeah, because on the cellular network, there is this separate queue for you and me, and so we're sort of isolated from everyone else. In the classical case, it's more difficult.
All right, let's thank our speaker one more time.